This is the third section of the vectors chapter, and this is on something called the scalar product. Now you may also see this referred to as the dot product. So it's basically the same thing. So it could be called the scalar product or the dot product. And what this allows us to do is to find the angle or the cosine of the angle between two vectors. Now, these vectors may be in 2 dimensions or 3 dimensions. So let's say we've got 2 vectors like this, which we'll call A and B. And let's say that this is the point, we'll call it X. It could be the origin, but we've got some point X there. And we want to find the angle between these 2 vectors. So let's put this angle here, let's call it theta, like this. And the dot product allows us to find the angle between these 2 vectors as long as these 2 vectors are pointing away from this point X. So notice this point here is like the vertex of the angle, and these 2 vectors, their direction, the direction is important. These 2 vectors are pointing away from the vertex of the angle. So we'll just write that down. That's an important point. Okay, so the scalar, we'll just put dot product or dot product, allows us to find the angle, and we'll call this angle theta, between 2 vectors. Let's write the word between properly. Between 2 vectors, this could be in 2 dimensions or 3 dimensions, that are pointing away, or their direction is pointing away from the vertex of the angle. Okay, now the reason why that's important, let's say for example I had 2 vectors that weren't pointing away from the vertex of the angle. So let's say I had a vector here, let's call this vector C here, and what if I had vector D and it was pointing this way, like that. Now when I find the angle between them, and I use the dot product or scalar product to do that, this is not the angle that I would be finding. It always finds the angle between the 2 vectors that are pointing away from each other. So actually, the angle that I would be finding, so if I carry D on, it points this way. The angle that I'd actually be finding is this one. Yeah, which actually means this one here, well, that would be, seeing as this is a straight line, yeah, this would be 180 degrees minus theta. So you can see what happens if you don't have the 2 angles pointing away from the vertex. You won't actually be finding that angle, be basically 180 degrees minus that. So these are both pointing away from this vertex here. This is the angle we'll find. If I have a diagram that's like this, actually this angle here would be 180 minus this angle over here. Okay, let's have a look at this example here. So it says find the angle between the 2 vectors A and B on a diagram. Now do you notice how that these 2 vectors, let's just draw this diagram again. We have this point X. Look at the direction of the vectors. There's my point X here. Here's A, here's B, and I've been told that this angle here is 20 degrees. If I want to find the angle between A and B, it's not actually 20 degrees. I need to draw the 2 angles that are pointing away from the vertex X. So B needs to be extended, and the angle between A and B is actually going to be this angle here. Okay, and as I've shown you on the previous slide, the way that we find that angle is that we just do 180 minus the angle on the other side. So that's just going to be 180 minus 20 So that actual angle between the two is 160 degrees. So again, as we said before, the direction of these vectors is important. Now, before we go through these two examples here, we're going to write down some important information and results about this scalar dot product here, and then it will make these questions that we're going to be doing a lot more straightforward. We'll know exactly what we're doing. Okay, so the first thing is, what's the definition of this scalar dot product? Okay, so the scalar or dot product of two vectors and we'll call those vectors A and B, is the length of A, so the modulus symbol says that the length of A times by the length of B times by the cosine of the angle between them. So this is the definition of the dot product. This is how we find the dot product. Now we actually want to find the angle between two vectors, so we'd probably rearrange that. So let's write this down. So when we write something like this, this is what the dot product, that's how it's written, A dot B. Makes sense, it's called a dot product, so we use a dot. So this is going to be an important, useful formula. So let's just highlight this here. So the bit that's the actual dot product is the bit on the left hand side where we've actually got the dot. So we'd say A dot B equals modulus of A times by the modulus of B, or the length of A times the length of B, times by the cosine of the angle between them. Now if we rearrange that so that we get the angle, we can say that the cosine of the angle between two vectors, remember they're still pointing away from the vertex of the angle, that would be A dot B, so write that down, A dot B divided by the length of A times by the length of B. Okay, now we're going to see how we can break this down a bit by looking at parallel vectors and perpendicular vectors. Perpendicular vectors, let's spell that right. So are there any special results if vectors are parallel or perpendicular with this scalar or dot product? Okay, so let's start with parallel vectors. So vectors are parallel, so they're like this. Okay. What can I say about the angle between the two vectors? Well, there is no angle, and we'll call these vectors A and B. So no angle between A and B. Yeah, so if this was vector A and this is vector B, there's no angle between them. Okay, so if there's no angle between them, that means that theta is 0. Now if I look at the left hand side of the scalar product, I've got cos theta. Now what's cos 0? So cos 0 is 1. Now if cos 0 is 1, and I'm looking at this expression here, it means that the top part equals the bottom part. So this leads us to this result, that A dot B, the dot product, is equal to the length of A times the length of B. So this is the result that we want. So if I've got two parallel vectors, then the dot product of those two vectors is equal to the length of the product of the length of those two vectors. Now let's say, for example, I'm looking at two vectors which are the same. So let's say that it was A dot A, for example. So it gives us another result. So A dot A, so these are two, these would definitely be parallel and they're the same length. Well, what's that going to be? Well, we're going to be doing the length of A times the length of A. and that will just be the length of A squared. Okay, so this gives us another result if I'm basically doing a dot product of a vector with itself. Okay, let's move on. Let's have a look over here at perpendicular vectors. Let's go for the same type of thing. So if two vectors are perpendicular, then the angle between them, or the angle between A and B, so we'll do like a little diagram again like we did before. And we'll call these two perpendicular vectors, one like this and one like this. We'll call one A and one B. A here, B here, so they are perpendicular. So the angle between the two vectors, well, that's just 90 degrees, which means that theta equals 90. And if theta equals 90, then cos theta, cos 90, well, that's 0. And again, looking at our definition here of the dot product, or its rearranged form here. So if this is 0, the only way this is going to be 0 is if the numerator here is 0. So this leads on to another result, which is if two vectors are perpendicular, A dot B equals 0. And we'll just highlight that result there. So now we've got that information, we can now go back to these questions and have a go at them. Now remember that I, J and K are perpendicular unit vectors. So I, J and K are unit vectors that are perpendicular. So I'll try and draw what they may look like. So remember, this is in 3 dimensions. So we've got our unit vectors like this. Yeah, so imagine this is 3-dimensional like this, and our unit vectors, I here, J here, and let's say K there. So you can see how they're perpendicular. So in part A, I need to work out what I dot J is. I dot J. So I'm using the formula here. So I want the length of each of those vectors. Now they're both 1 because they're unit vectors. So this is equal to 1 times by 1 times by the cosine of the angle between them. So these are all perpendicular, these vectors. So this is going to be times by cos 90, not co 90, cos 90. Now the thing is, cos 90 is 0, isn't it? So you're going to have 1 times by 0. So I dot J is just going to be a value of 0. Okay, let's move on to part B. So we've now got K dot K. So we do the same thing again. We want the length of the vectors times by the angle between them. So that's going to be 1 times by 1. Now the angle between them is 0, isn't it? So cos 0. Now cos 0 is 1. So you've got 1 times 1 times 1. So the final answer is just 1. Now we could have also worked out this answer here by using this definition. Yeah, now another way of doing it would be saying, well, it's the length of K squared. Okay, so alternatively, we could have said, right, K dot K is equal to the length of K squared. Now the length of K is 1, so 1 squared, that's 1. So we get the same answer either way. And then part C, I can see that I've got 4J dot K plus 3I dot 3I. So I'm going to work out the two dot products separately, and then I can add them together. So 4J dot K, right, so we're going to use this again. Now this time the lengths are not all going to be 1, so 4J, the length of 4J is just 4. So So it's going to be 4 times by the length of k, which is 1, times by the angle between them, and they're perpendicular, so that's going to be times by cos 90. Cos 90, so that's the first bit, plus then the length of the vectors, they're both 3, times by the angle between them. Now they're parallel, aren't they? So the angle between them is 0, so times by cos, not cos 90, cos 0. Or I can use the definition here about the length of the vector, which will be, or the length of 3i. Actually, it will just be the length of the vector 3, wouldn't it? Be the length squared. Yeah, we'll see if we get the same result by not doing that way. So the first bracket, cos 90, so 4 times 1, cos 90 is 0, so the whole first bracket just becomes 0. And then we're going to have 3 times 3 times by cos 0, which is 1. So all of that just gives us a final answer of 9. So you can see that if we had done the length squared, we would have got the same answer, whether we had used this rule down here, this result down here, or we had used the definition of the dot product. So let's just highlight the answers before we move on. So 0, 1, and 9. Okay, so here we've got, given that vector A equals this and vector B equals this, we want to prove that A dot B is given by that. So here we're going to be proving the result for the dot product, so we can work it out directly. So before, what we've used is the length of the vectors times by the angle between them. There is a way to work it out directly. Now, before we prove this result, there are a few things we need to know beforehand that are going to be useful in doing this proof. So I'll just put hints here. Okay, the first thing that's going to be useful is to remember that if I've got something like I dot I or J dot J or K dot K, okay, that's going to be 1. Yeah, from what we did before, the length of those vectors times by the angle between them, which is 0, we'll get 1. So that's the first thing. The second thing is that any perpendicular unit vectors, so like I dot J or I dot K, or what else have we got? So we've got J dot, it could be the other way around, J dot I or J dot K, or what have we got left? K dot I think this is going to be all of them, or K dot J. Okay, any perpendicular vectors like this is going to be 0. Yeah, when we do the dot product of them, because remember, if they're perpendicular, the angle between them is 90, and when we use the definition of the dot product, A dot B, so I'll write this down, because that angle between them is 90, cos 90 is 0, so it will become 0. And another result is that when we do the dot product, it's something that's called distributive. Okay, now something that's distributive is a bit like expanding brackets, so I'll just put it's like expanding brackets. There are certain things in maths which are distributive, which means you can expand brackets. Yeah. So what that means is, if I get something like this, for example, if I had A plus B, so I had vectors like this, dot C plus D, because the dot product is distributive, I can treat this like expanding brackets. So what would happen is this would become A dot C, yeah, just like expanding brackets, plus A dot D plus B dot C plus B dot D. Yeah, so this thing that's when something is distributive, we can treat it like expanding brackets. Right, now armed with all of that information, let's go through this. So A, the vector A, I can write as this: A1I plus A2J plus A3K, and the vector B can be written as B1I plus B2J plus B3K. Now that means that A dot B is equal to A1I plus A2J plus A3K dot B1I plus B2J plus B3K. Okay, now how are we going to deal with this? Well, we're going to use this, what we call this distributive law, which means we're basically going to treat it like expanding brackets. So there is going to be a lot of multiplying out. So I'm just going to draw some of the arrows in. But basically, we're going to have all of these things multiplied together. There's going to be another 3 arrows. Let's do these in a different color. Let's go for green. And then all of these here. So everything here, 9 multiplications that we need to do. So I'll start a few off, then I'll pause it and finish it. Right, so what are we going to have for A dot B? Right, so we will have A1 I dot B1I, yeah, plus A1I dot B2J plus A1I dot B3K. So hopefully get the idea. Yeah, so I'll just do 1 or 2 more before pausing. So A2J dot B1 I, putting a dot in the wrong place there, let's get rid of that, plus A2J dot B2J, and so on. Okay, so these are all the results here. Now we're going to go back to what we said here about vectors here, unit vectors, which are either parallel or perpendicular. Now all of the ones where we've got perpendicular unit vectors multiplied together, it's going to become 0. Now where are they? Now I can see there's one here. Yeah, there's another one here. These 2 perpendicular. Then this one. But in the bottom row down here, here's 2 perpendicular vectors. And here's 2 more perpendicular vectors. Now what's going to happen is we know those dot products are 0. So all of these become 0, so I'll cross them out. Yeah, they're all 0 because we're doing a dot product of 2 perpendicular vectors, and then we know when we do that the result is 0 because cos 90 is 0. Now that leaves us with these 3 here. Now with these ones, these are going to be left, and we know that when we do the dot product of I, or J and J, or K and K, it's going to be 1. So actually all that's left is like the coefficients of these vectors. So A1, B1 plus A2, B2 plus A3, B3. Now that's what we needed to prove if you have a look in the question. So we can, it's I'll say it's been proved as required. Now, how might we use this? Here's an example of how we might use this. So let's say I had two vectors, and one vector was the vector 5, 4, minus 2, and another vector was the vector 0, minus 1, 4. And I want to find the dot product of those two vectors, or the scalar product of those two vectors. Well, that means all I do is 5 times 0 plus 4 times negative 1 plus negative 2 times by 4. Negative 2 times by 4. And that's all we need to do. So you notice how we sort of multiply each pair of numbers together, and we just add them up, find a total of that, and it gives us the dot product. Now this is going to be 0, minus 4, minus 8, so we get dot product is equal to negative 12. Now this is useful because this is going to allow us to find the angle between two vectors, because this is the rearrangement of the what the definition of the dot product is. And now we know how to find this value up here. Yeah, so now we know how to find that, and we know how to find the length of the vector. We can then use that to find the cosine of the angle between any two vectors, assuming that is that they actually meet at some point. Okay, so now we know the definition of the dot product, or how to find a dot product. We can now find A dot B. So A dot B is going to be 8 minus 5 minus 4. Now I often prefer to write the vectors in columns. I just find it more straightforward than writing things in a long row. So yeah, this is going to be 8 times 5 plus negative 5 times by 4 plus negative 4 times by negative 1. So that will be 40 minus 20 plus 4. So that will be minus 20 plus, 20 plus 4. So that will give us 24. So that's the scalar dot product, or dot product of A and B. And part B, it says find the angle between A and B given our answer in degrees to 1 decimal place. So we can find the cosine of the angle between them, and that is A dot B over the length of A times the length of B. So A dot B, well, we've already worked that out, that's 24, divided by the length of A. Let's do the working over the side here. So the length of A, that will be the square root of 8 squared plus negative 5 squared, or just 5 squared, plus negative 4 all squared. So that will be the square root of 64 plus 25 plus 16. So that will be, I think that's 105. So root 105 is the length of vector A. Then we'll do the length of B, and that will be the square root of 5 squared plus 4 squared plus 1, negative 1 squared. So the length of B, that's going to be square root of 25 plus 16 plus 1. So that's 41, 42. So root 42. So they can go at the bottom here. So root 105, root 42. So that will be the cosine of the angle. So the angle itself is going to be the cos inverse of 24 over root 105 times by root 42. Now if we do that on our calculators, we'll get something like 68.8136 ... That's an acute angle, and it says give an answer to one decimal place, so that just rounds to 68.8 degrees. Okay, so here it says given that we've got these two vectors A and B, I'm probably going to write them in column vectors, find the angle between them given our answer to one decimal place. So we need to find a dot product of A and B and a length of A and B. So let's start with the dot product. So that would be -1, 1, 3. So that's A written as a column, dot 7 minus 2, 2. So that will be -1 times by 7 plus 1 times by -2 plus 3 times 2. So that will be -7 minus 2 plus 6, and that is -9 plus 6, that's -3. So that's the dot product. So let's now find the length of A and the length of B. So the length of A will be the square root of -1 squared plus 1 squared plus 3 squared. So what will that be? 1 plus 1 plus 9, so that's 11. So root 11. Then vector B, the length of that vector. So that would be the square root of 7 squared plus -2 squared plus 2 squared. So it's going to be 49 plus 4 plus 4, so 49 plus 8, which is 57. Okay, so now they can go into the formula. Let's find the cosine of the angle. So A dot B, -3, over the length of A times the length of B. So that's root 11 times by root 57. So then the angle is going to be the cos inverse of that. So -3 over root 11 root 57. That will give us theta equal to 96.88104, which means that theta equals, now what's it, one decimal place, 96.9 degrees to one decimal place. Now here it says, given that the vectors A and B are perpendicular, find a value of lambda. So lambda's here, this unknown. Now we know that if A and B are perpendicular, then their dot product is equal to 0. So we'll just write that down as a reminder. We did say that earlier. So if A and B are perpendicular, their dot product, A dot B, equals 0. Now if A dot B equals 0, what that means is that 2 minus 6, 1.52 lambda equals 0, which means that 2 times 5 plus -6 times by 2 plus 1 times by lambda equals 0. So this should be nice and easy. So I'll have 10 minus 12 plus lambda equals 0, which means that lambda equals 2. If we work out that very simple equation. Right, so I've got these two vectors here, A and B, and I want to find a vector which is perpendicular to both of them. So the first thing I'm going to do, I'm going to call this vector C. So I'm going to say let C, so this is the vector I want to find, be perpendicular to A and B. So that's the first thing. Now if it's going to be perpendicular to both of these, that means that the dot product of A and C is 0 and the dot product of B and C is going to be 0. So what I'm going to do, this vector C, let's just call it x, y and z, or x, y and z. So I need to basically work out what these are. So let's start first of all by working out the dot product of A and C. So it's going to be -2, 5, -4 dot x, y, z, or x, y, z if you're American. So that gives me -2x plus 5y minus 4z equals 0. So there you can see I've got an equation which is going to be useful. And now I'll do the same and find b dot c. So that's going to be 4, -8, 5 dot x, y, z. And that will give me 4x minus 8y plus 5z equals 0. So here is a second equation. Now we've got a problem here because I've got two equations with three unknowns and they can't be solved without a third equation. So we're just going to write this down. So since, and this problem is going to come up at other times when we do these questions with vectors where you're going to have three equations or two equations but three unknowns. But since we have three unknowns, we need to do something to help us solve this, but only two equations. Okay, we have to set x, y, or z to a non-zero value. So we need to choose a value for x, y, z. Okay, so that we can solve. Yeah, so we actually need to pick a value for x, y, or z. And I'm going to choose and make x equal to 1. So we want to choose easy values so that we're able to solve them easily. Okay, so if I make x equal to 1, then the first equation here, that will become -2 plus 5y minus 4z equals 0, which I might want to write as 5y minus 4z equals 2. And then the second equation, so this one here, making x equal to 1, I'll have 4 minus 8y plus 5z equals 0, which again I could write as -8y plus 5z equals -4. Now I can solve these simultaneously since I've made x equal to 1. So I will take the first equation and multiply that by 5, and the second one multiply that by 4 so that I can get these coefficients here the same. So if I do that, I will now get these equations, 25y minus 20z equals 10, and -32y plus 20z equals -16. So these I will add together, and if I add those two equations together, I'll end up with -7y equals 6, which gives me a value of y equals Oh, sorry, negative 7 equals negative 6. I beg my pardon. So y equals 6 over 7. Okay, what we'll do, we'll sub that into the 5y minus 4z equals 2 equation. So that'll be 5 times by 6 over 7 minus 4z equals 2. So from that, if we solve it, we'll get z equals 4 over 7. Now, since we set x equal to 1, it gives us this vector 1, 6 over 7, 4 over 7. So we could write that as our answer. Or we could take the 1/7 out, like this, and then write it as 7, 6, 4, or actually any multiple of that. Yeah, because all we're doing is changing the length. It's still going to be perpendicular to both. So we could take the 7th out, and actually we could just write, if we used I, j and k, we could just write 7i plus 6j plus 4k. And it's useful sometimes to take that fraction out so that we get some nice whole number answers rather than fractional ones. So any one of these will be fine as answers. Now, if we had chosen a different value to make x, or we had made, let's say, y equal to 1 or z equal to 1, we would have got basically an equivalent answer, just maybe a multiple of what we've got here. So we've got these points A, B, and C. So A is this one. Whenever it says respectively, it just means in the same order. B is going to be this one, and C is going to be this one here. And what we want to do is to find AB and AC, and then find a dot product of them. Right, so the vector AB is going to be, now we can do this by working out the difference, the jump from A to B, yeah, or we can do vector B minus vector A, and then A to C, we can work out the jump, or we can work from A to C, or we can do vector C minus vector A. I prefer the jump method. So if I work out the jump from vector A to vector B, so the first number goes from 2 to 5, so that goes up by 3. Second number goes from -1 to 1, so that goes up by 2. And then the third one goes from 1 to 7, so that goes up by 6. Now, to go from A to C, using the jump method, so 2 to 6 goes up by 4, -1 to -3 goes down by 2, and 1 to 1, well, that doesn't change. So now we can do the dot product of AB and AC. So 3 to 6 dot 4 minus 2, 0. So that would be 3 times 4 plus 2 times by -2 plus 6 times by 0. So that would be 12 minus 4 plus 0. So we get a dot product of 8. Yeah, oh, and that's it. That's all we need to do is find a dot product. So that's that bit done. Now we can move on to part B. This hence or otherwise find the area of triangle ABC. So here a sketch might be useful. So the vertices of the triangle are A, B, and C. And I know these vectors, don't I? I know A to B, and I know A to C. Yeah. So I could work out the angle between them. And if I find the lengths of these sides here, then I can use half AB sine C to find the area. So I'll just write that down. Area of that triangle is going to be half AB, so A to C, yeah, half AB sine C. So sine C, so that'd be the angle between them there. So it's just a matter of finding the lengths of these vectors and then using the dot product to find the angle between them. Right, so let's first of all find the length of the vector AB. So that's going to be the square root of 3 squared plus 2 squared plus 6 squared, which is the square root of 9 plus 4 plus 36. Now, what's that? 49. Right, Sandy. So the length of that side is 7. Now the length of A to C. So A to C is going to be 4 squared plus negative 2 squared plus 0 squared. So that's going to be 16 plus 4 plus 0. So we've got root 20. We'll leave it like that. We don't need to simplify it. Now we need to find the angle between these two vectors. Now actually then we could just go straight to the cos inverse part, and then it's going to be the dot product, which is 8, we worked that out in part A, divided by what's the length of them, so that's going to be root 49.7 times by root 20. Okay, so we'll work that out on our calculator and we'll get 75.193 degrees. So the area of this triangle, half A B sine C. Now here where I've got this angle, I would be using the answer button. Yeah, so I get the exact value. So working that out, we'll get 15.13274, which will round, and we'll give our answer to 3 significant figures. So that'll be 15.1. There are no units for lengths here, so we'll just put square units, and that's 3 SF for that. Okay, you should now be able to do exercise 9C on pages 183 to 184. So let's just do a recap of what we've done. So we have found the dot product, which allows us to find the angle between two vectors. So we'll just mark that in like this, and we have the cosine of the angle is A dot B over the length of A times by the length of B. Now what we said was, if for example vector A is let's say x, y, z, and vector B is ABC, then the dot product is equal to AX plus BY plus CZ. There were a couple of results we found. So one of them was that if vectors A and B are parallel, if vectors A and B are parallel, then the dot product of the vectors is just equal to the length, or the product of the length of the vectors. And an extra rule that goes with that is that if you're doing A dot A you'll just get the length of A squared. If A and B are perpendicular, then what we have is A dot B equals 0. And then we looked at some stuff with unit vectors as well. These unit vectors I, j, and k. Okay, so I, j, and k. So what results did we have? Well, if it's I dot I, or j dot j, or k dot k, that will be equal to 1. And then any perpendicular vector, so for example, I dot j, I dot k, or j dot k, or even the other way around, that will give the other 3, that will be equal to 0.